All right, so now we're going to talk about what is called Richardson extrapolation, which is a way to take this symmetric finite difference approximation of the derivative and then by appropriately evaluating it for different step sizes and combining the results in a sort of informed way, you can get a approximation of the derivative which converges much faster than what you expect it to. Okay, so let me sort of give you sort of an idea of the method. It's like, and we'll go on. So, all right. So this is Richardson extrapolation. And then the goal is to obtain a numerical formula with sort of arbitrary high order of accuracy. Okay. All right. So if you use the sort of the complete Taylor expansion, right? Instead of the ones where you've truncated it and put down the remainder term, sort of the okay. So you can if you use the complete Taylor expansion of f of x minus h and f of x plus h, right? We obtain the following. So you can check that the first derivative f prime at x can be approximated by f of x plus h minus f of x minus h over 2h with the error terms which we saw before. But what I'm going to do is I'm going to look at the higher order terms that's like in the error expansion. Okay, so so you have h squared over 3 factorial as before, and this involves the third derivative of f at the point x plus h to the 4 over 5 factorial, fifth derivative of f x plus h to the 6 over 7 factorial, seventh derivative of x, and so on. Okay, the thing you really need to sort of take away from this, if you will, is that the error looks like h squared, h4, h to the 6, and so on. So that even powers of h. So depending on the method, it's like these expansion, the higher order terms in expansion will look different. But the basic idea, it's like of Richardson extrapolation, is that you take this computable approximation, you evaluate it for a particular value of h, you evaluate it for some other value of h, and you combine it in a smart way so that you cancel out the leading order error term, so that the resulting combination, it's like of the values for different h's, give you something which approximates the left-hand side, which is the first derivative in this case, to a higher order of accuracy. So that's sort of the high-level motivation for this. So we're going to treat this abstractly in the following way. So the thing which I'm trying to compute, I'm going to call L, and L is going to be some computable thing, which I call phi 1, and there's a parameter, which I call h, right? So phi 1 of h you should think of as this expression here, okay? And then there's an error, it's like expansion, which I call a21 h squared plus a41 h to the 4th plus a61 h to the 6, and so on. Okay, so again, the error is dominated as h goes to 0 by this leading order term, which is big O of h squared. Okay, so for the remainder of this discussion, it's like even though this is motivated by trying to take the symmetric finite difference approximation of the derivative, it's like and then constructing something which scales better than O of h squared, maybe O of h to the 4, right, and so on. we're going to treat this more abstractly because, again, the basic idea of Richardson extrapolation applies beyond just this specific example. So let's, again, think about it in this sort of more abstract notation here. Okay, so given this, right, I'm going to ask, well, what can I do if I evaluate this method with a different value of h? Okay, so the question, so this is the error, I guess, is big O of h squared, right? I want to use this to construct an approximation of L, which is accurate. So if not h squared, the next term is OH to the 4. So let's try that, right? 2 big O of h to the 4. Okay. So how am I going to do this? So I know what happens. It's like in the error expansion for h, all right? So what I can do is to, everywhere I see a h, I can replace it with h over 2 and then see what happens, okay? All right. So let's call that star, right? So I replace h in this equation with h over 2, right? And let's just see what happens. So L is equal to phi 1 evaluated at h over 2, right? Plus a21, every time I see a h, I replace it at h over 2, h over 2 squared, right? Plus a41, sorry, h over 2 to the 4th power, and so on. I don't really want to worry too much about it. Okay. Okay. So, right. So what can I do here? Right. I can. What I basically want to do, if you think about it, is I want to cancel out the leading order error term with this, okay? So these two terms, right, differ by a factor of 4, right? Because you have h over 2 squared, so this is going to be h squared over 4. This is a h squared. So if I multiply this entire equation by 4, I will have a term a21h squared, which I then can cancel. It's like this term here. So that's basically the strategy. So I'm going to multiply this entire equation by 4. So that's 4L is equal to 4 phi 1 h2 plus a21, right, h squared plus a41. Okay, so this is 1/4 h to the 4 plus high order terms, right? Okay, so now I'm going to call this equation 2. Okay, so I can subtract equation 2 from equation 1. Right, this gives me 4L minus L on the left-hand side is equal to 4 times phi 1 evaluated at h over 2 minus phi 1 evaluated at h. And this term cancels out this term, so that disappears. Okay. All right, and then yes, so this is okay, where was I? Okay, and then this is okay, so plus 1/4 minus 1 a41 h to the 4 plus higher order terms. Okay. So, and then I can divide everything by 3, right? So I divide by 3, right? So this is 4L minus L is 3L, so that's L is equal to, okay, so let's write it this way, 1/3 4 phi H2 minus phi 1H. Right, minus 1/12, actually no, so that's 3/4, 1/4. It's 1/4 if I'm not mistaken. Okay. All right. So, so the way to think about this is that this is now my next approximation. Instead of phi 1, I'm going to call this phi 2 of H, right? And so this is equal to phi 2 of H plus now an error term A for 2 H to the 4 plus A 6 2 H to the 6 plus so on. Okay? So hopefully you get the idea. It's like what's involved, right? You evaluate the computable approximation with two different values of H. You write down, it's like what the implications are at the level of the error expansion. You multiply, it's like the equations sort of throughout so that the leading order error terms are the same. And then you subtract the two. And then you divide appropriately so that the left-hand side is the one thing you care about. So, so this is, again, the basic idea behind Richardson extrapolation. So what this is basically telling you is that, so what it's telling you is the following, that if, back to our example, if f prime of x is equal to f of x plus h minus f of x minus h over 2h plus something which is order big O of h squared, and in particular you happen to know what the further terms are. It's like, so in the analysis we had, it's like we said that it's not just that the terms are sort of, you know, some constant of h squared plus some constant of h4 and so on, right? I mean, it's like, so there's an expansion involving even powers of h in this case. It's not always the case that's what's happening, but in this case it is. And then, you know, the claim is that if you think of this again as one type of method, then if you take this second order term, which is defined to be, right, again, 1/3 4 times phi h over 2 minus phi 1h. Okay, and I can expand what that is, right? So that's 1/3 4 times f evaluated at x plus h over 2 minus f x minus h over 2 over h, right? That's what this is, minus, again, f of x plus h minus f of x minus h over 2h. This thing, right, is f prime of x plus an error which is now h to the 4 instead of h squared. Okay, so that's what this Richardson extrapolation idea does. And the idea, of course, is that you can keep going, right? So it's not necessary for you to just stop at this second order case. You can combine phi 2's for h and h over 2 to cancel out the next leading order error term, which is of order h to the 4. And then what the method you end up getting is now order h to the 6, right? So you can keep doing this. Okay. So let's just see an example of doing this one more time, right? So this is what I'm calling phi 2 of h is for the specific example we looked at. I'm just going to erase this, and I'm going to look at what the next expansion is. Okay. So this is saying that L is equal to phi 2h plus a4 2h to the 4 plus a6 2h to the 6 plus so on. I'm going to do this again for a different h, so h over 2, for example, right? This becomes a4 2, right? So 1 over, well, h to the 4 over 16, right, plus a6 2, right, h to the 6 over 64, plus so on. All right, so again, I want to multiply the second equation, so by a factor of 16 now, so I get an a4 2h to the 4 term, which agrees with this a4 2h to the 4 term in the first expansion. So I take 16 times L is equal to 16 phi 2 h2 plus a4 2 h to the 4, right, plus a6 2 h to the 6, 1 over 4 h to the 6 plus higher order terms. Okay, so I can do the same trick again. 16L minus L is 15L, obviously, and this is equal to 16 phi 2 h over 2 minus phi 2h, right? That term now cancels out the other error term, and then plus you're going to have some, let's see, right, it's going to be minus 3/4 again, a6 2 h to the 6 plus higher order terms. Okay, so that means that L is equal to 1 over 15, 16 times phi 2 h over 2 minus phi 2h, right? And then there's an error term which is big O of h to the 6 now. And this is what I'm going to call phi 3h, right? So hopefully you start seeing the pattern. You can keep doing this repeatedly to get higher and higher order. And I guess I should remark that what you're going to have to do here, right, is that you're going to have, so think about it, if you were, if you're doing the function evaluations, you'll see that each time you have to take, it's like smaller and smaller steps, if you will, of the original method, right? So this method here, it's like, which is phi 2 for h over 2, you have to remember that phi 2 itself for h already involves phi 1 at h and h over 2. So phi 2 at h over 2 involves phi 1 at h, h over 2, and h over 4, and so on. So you have to be mindful of that. Actually, sorry, phi 2 at h over 2 involves phi 1 at h over 2 and h over 4, right? But so the full method itself, right, will require you to evaluate the original method at h, h over 2, and h over 4. Okay. So in the very first iteration, you for phi 1, it's like you just obviously evaluate phi 1 at h. When you have phi 2, you evaluate phi 1 at h and h over 2. At phi 3, you evaluate phi 1 at h, h over 2, and h over 4. So it's not necessary for you to have this factor be 1 over 2, right? You could be anything you want. It could be 1/3, 1/4. It is a choice which you can make, right? All right, so with that in mind, then, it's like we can figure out what the general form of this. You'll see that it's sort of fairly obvious what the general form is after you've worked through a few of these examples by hand. So in general, at step K, what we have is that you have L is equal to phi k h plus a 2k k h to the 2k plus higher order terms. and then you have 4 to the k. L is equal to 4 to the k. It's like phi k h over 2 plus a 2k k h to the 2k. All right, and higher order terms, and then so you have L is equal to 1 over 4 to the k minus 1 phi k h over 2. Sorry, there's a factor of 4k here. So 4 to the k phi k h over 2 minus phi k h, right? And again, it's like these factors are chosen so that these error terms, leading order error term agrees with this one here, right? And so when you take the difference, they cancel. And then the remainder is big O of h to the 2k plus 2. Right, so that's the basic idea. All right. So so again, it's like, let me sort of say a bit about that, right? So you recall, evaluating, and I think I should say that this obviously is phi k plus 1 h, right? So so evaluating phi m plus 1 h involves evaluating phi m h over 2 and phi m h, right? And you can sort of see by induction, I'm not going to sort of go too much into details, but it's sort of fairly easy to set up the induction that you eventually get that evaluating phi m plus 1 h involves evaluating phi 1 at h all the way up to phi 1 at h to the h over 2 to the m. Okay. Right. Yes, that is correct. Okay, that's easy to check just to make sure that you have the right thing, because when you have m is equal to 0 corresponding to phi 1, right, then this becomes 2 to the 0, which is just the h, so there's only one term, right? So that's consistent with what you expect. Okay, so that's the basic idea behind Richardson extrapolation, and then we're now ready to talk about how to set this up. It's like as an algorithm, all right? So let me show you how to do that. Okay. Okay, so I'm going to construct a matrix basically. It's like in this setting. So let d n comma 1, right, be defined to be phi 1 for h over 2 to the n minus 1. Okay, and then n will go from 1 to m plus 1. Okay, so right. So if you recall, it's like that's you need to evaluate. It's like the underlying method for different h's, h over 2, h over 4, up to h over 2 to the m, right? In order to get what you need. Okay. So that's sort of the first row. So this is going to give you phi 1, and then the next columns, if you will, is going to give you the phi 2s, phi 3s, and so on. Okay, so then D and K, right, is going to be just phi K H over 2 to the n minus K. Okay, so with that thing, it's like then I can write down the relationships between phi K plus 1 and phi K in terms of the entries of this matrix. So D n K plus 1 is equal to 4 to the K over 4K, 4 to the K minus 1 times D n K, right, minus 1 over 4 to the K minus 1 D n minus 1K. Okay, so that's the relationship. And then once you have these things, right, then you can write down an algorithm for this. Okay, and I should say this sort of sets up some sort of triangular matrix, right? So you have D2, 1, D2, 2, right? D3, 1, D3, 2, D3, 3, and so on, okay? And then eventually you get, well, anyway. All right, so let's not worry too much about it. Yeah, so you get some sort of triangular matrix like this, and then I can write down the pseudocode for this. Right? So what I want as inputs are sort of x, right? The point which I want to evaluate, that's like the derivative at, the times your initial step h, and then m, which is sort of the how deep I want to go in this recursion for the Richardson extrapolation. And then you do for n equals 1 to n plus 1. You do the following loop, right? D n1, right, is just equal to the original method, phi x h over 2 to the n minus 1, right? So this is really just f at x plus h over 2 to the n minus 1 minus f of x minus h over 2 to the n minus 1 over 2 times h, right, which is 2 to the n minus 2. Okay, actually, I'm sorry, n, actually, my bad. Okay, 2 to the n. Okay, all right, and then you end the do. So this sort of fills in the first column, right, with just the symmetric finite difference approximation of the derivative with different values of h, right? So h, h over 2, h over 4, and so on. Then you go through to fill in the columns, right? So for k equals 1 to m, you do the following. For n equals to k plus 1 to m plus 1, you do this. So this second one has to do with the fact that as you go for each column, it's like the matrix is lower triangular, so the starting entries sort of go further down, right? So that's why this index is lower. Okay, and then d n k plus 1 is equal to d n k plus d n k minus d n minus 1 comma k divided by 4 to the k minus 1. So this has been written in a slightly different way, right? So that you have this value, it's like, and then there's a slight update, right? So that improves the stability of the method slightly, okay, as opposed to this particular formulation. Okay, and then you end the for, okay, and then you end another for loop, and then you, I'm sort of out of space, let me just sort of say, the last thing is to output the thing, so you output d n comma k, all right, for n between 1 and n plus 1, and k between 1 and n. So you output the entire matrix. It's like, but obviously, you know, if if all you care about is the final answer, you just want this sort of bottom rightmost entry of that matrix. Okay, So that's the basic setting. It's like we're doing Richardson extrapolation. Again, the basic idea, at least in the context of the symmetric finite difference approximation of the derivative, is the first column tells you it's like it's like the again sort of finite difference approximation for different h's, different values of h over 2, h over 4, and then it's like these construct sort of these higher order phi's. It's like so this is the phi 1, the phi 2, the phi 3, and so on, right? So that's basically what's happening here. So let me just stop here for now, so we'll pick it up in a little